Welcome everybody. I'm Fredrik. I work for JuliaHub. I'm also the idiot in the pictures there if you have found me on Discourse or GitHub. And today I will talk to you about linear analysis and how we do that in ModelingToolkit. All right, so we'll start by talking about why we might want to do a linear analysis. We typically do a linear analysis when we have small deviations of our dynamical system from an operating point. So I had drawn a nonlinear function there and a linearized version of that function. And the operating point is the point in which we perform the linearization. So it's the point in which we operate our dynamical system. And this kind of small deviations from an operating point typically occurs when we have, for instance, vibrations. So if you think of a building vibrating, hopefully the vibrations are not too large. In electronics, we often do this with a small signal model. And in a control system, we might experience this because the controller is actually responsible for making sure that the deviation is small. So deviations are very often small by design. All right. And the workflow here, this is a messy slide, but we start on the far left with a nonlinear model. So this would be our ModelingToolkit model. We perform linearization using forward diff or symbolically. Then we obtain a large linear DAE model typically. We can perform some simplification on that if we would like, and then we arrive at a small linear ODE model. And then we perform more analysis on that linear model, and we arrive at some insight. So the very first step is to look at the interface to linearize. It's a function in ModelingToolkit. It takes the system, it takes a list of what you consider to be the inputs and what you consider to be the outputs. And it takes an operating point. So the operating point OP here is a dictionary that maps variables to values. And then it returns to you four matrices, A, B, C, and D. So those would be the four matrices in the linear state space representation you see in the bottom there. And this state space model now operates in delta coordinates, so in deviations from the operating point. And it also returns to you a simplified ModelingToolkit model. The next step is to perform the actual linearization. For that, we use forward diff. So we start with a system that is nonlinear. We have some dynamics function f that is a function of state variables x, algebraic variables z, some input variables u, and perhaps of time. And there are some algebraic equations and perhaps an output equation, y is equal to some function also. And after the linearization, we have this messy system on the right, but it's just a bunch of Jacobians of these three functions with respect to the arguments. The next step is to transform that to an ODE system. And I show you the code here just to highlight that it's actually just linear algebra to do that. It's very simple. If you don't have any algebraic variables, most of these things are actually of size 0, so then it's exceptionally simple. But even if you have algebraic variables, it's just linear algebra. Sometimes ModelingToolkit will fail to spot certain patterns in the simplification, and then you actually end up with a non-causal system, even though you expect a causal system. So a non-causal system in this context is a system that performs differentiation of the input. And we typically don't want that. So if we end up in this situation, we have a interface package, control systems MTK, that internally makes use of another package called descriptor systems that can perform another step of simplification for you to result in a causal system in the end. And the control systems MTK also contains a function called named SS for named state space. And that's kind of a convenience function that internally calls the linearization. And then it packages this into a structure that contains the linear state space system, and it keeps track of the names of the inputs and the outputs and even the state variables. So I will call this a convenience function in one of my examples a bit later. So we will have a look at a few examples of what we can do with this functionality. We will perform a modal analysis of a simple system, and then we will do some control system analysis. So mode analysis is not only an academic example, it's practically relevant. So here we see, on the far right, we see a building, and maybe there is some wind affecting that building, and it swings back and forth in the wind. And if we have too much swing back and forth, the people on the top floor will be nauseous. So we don't want that. So engineers will try to perform an analysis and figure out whether or not our design has an acceptable kind of vibration pattern. We can also do this for a bridge. So we have a bridge in the bottom right there. And if we think of a bridge as a kind of a flexible structure, that will also kind of flex in the wind and as trucks pass over it and so on. And it might be able to flex in many different patterns. And these patterns, we call them modes, and they have certain shapes. So maybe it will flex up and down, or maybe it will flex a bit like this and so on. And on the left, we have a drivetrain. So think of this as a drivetrain in a car or a truck, something like that. We have some generator or a motor that is acting on the, trying to drive the truck forward. And it's acting through some transmission. And that transmission is maybe slightly flexible. So you can look at this as two masses connected by a spring. And we might be interested in analyzing the mode shapes of this system. So here I have a ModelingToolkit standard library example. There is a QR code if you want to look at it. I've written a little function that just allows me to connect an arbitrary number of masses and springs. And once I have called this function, we see we have a, can I point here? Yep. We have inertias and springs and dampers. And I say inertia because it's a rotational example. And then I just connect n number of those. And in my example here, I will use 3. ModelingToolkit will give me something like this. It looks like a lot of equations, but that will mostly simplify down to a fairly small system. And once I have called this named SS function that performs the linearization inside, we see we end up with a system with 6 state variables. So 3 masses, they have 3 positions and 3 velocities. And this function takes the model as the first argument, then it takes a list of inputs, and in this case it's a single input, it's a torque I applied to the first mass, and my outputs are the velocities of the 3 masses in this example. And we see we have the 4 Jacobian matrices A, B, C, and D here. And this named state space system also keeps track of the names. So we have certain input and output and state names here. All right, once we have such a linear system, we can plot the frequency response. So here we plot something called a Bode plot. There are 3 curves in this plot for the 3 different masses. And we see that they resonate at different frequencies. So if I perturb this system at a particular frequency, we will get a very large amplitude in the output. But we also see that there are certain frequencies where one of the masses is standing completely still. So the blue mass here, the first mass, if I perturb it at exactly this frequency, that mass will actually not move at all. And we will look a bit deeper into that. We can also say what happens if I hit this system with a hammer. So I compute an impulse response. And an impulse response is an infinitely large input force for an infinitely short time. And then the system will swing like this, the 3 different masses. We can try to ask about something called a damp report. So control engineers might be interested in this. Where we show the different poles, or if they are complex conjugated, we show the pole pairs. They have certain damping ratios and natural frequencies, and they might be associated with time constants. We can plot the mode shapes. So here we have 3 mode shapes. There is actually also a visualization here or an animation on the right. So this system tend to like to vibrate in one of these 2 modes. And the last mode is a rigid body mode. So it just means that all of them moves together without any vibration. So we can plot them we can plot the mode shape in the top there. We see the first one says that mass number 1 and mass number 3, when they go in one direction, the second mass goes in the other direction. And that's the animation we see on top there. And we can simulate that in time also. We see exactly the same pattern. So you can imagine that if this would be a bridge, you might divide the bridge into finite elements, maybe a very large number of those. But then you will have these kind of mode shapes that indicate that the bridge will sway like this, for instance. So this is a very common analysis you might want to do as an engineer. We can also have a look at the control systems example. Here we will make use of the ModelingToolkit standard library to assemble a model. And there is a talk on the standard library happening later today, so I encourage you to check that out if you're interested. we will assemble a model of a DC motor. So here is a kind of a picture of a bunch of different electrical motors. The final model we will assemble is a feedback loop here. So we have P for process or plant, so that's the thing we would like to control. And C is our controller. So C is the guy that typically makes sure that deviations are small from the operating point. In this case, the controller will just be a very simple PI controller. And the block here, P, it represents the motor. It has some electrical component, a resistor, inductor. It has an electromotorical force, and then it has some mechanical components. So this is kind of a multi-domain model that has both mechanics and electronics. I will not show the creation of all the components. You can refer to the Modeling Toolkit standard library talk for that. But here we have a number of connections. So these connections form kind of the arrows you see here in the feedback diagram. It also forms some of the connections that happens inside of the P block. But an interesting point among these connections are that some of them have been given names. So some of these connections have a symbol as kind of the middle part in the connection. And the reason it's in the middle is to signify that this name belongs to the connection itself. So it belongs to kind of the lines rather than to any of the variables. And these analysis points are kind of small magical objects that behave in different ways depending on what you're asking the system about. So if you're just simulating the system, it's like they were not even there. They just disappear. But if you are asking for some interesting linear analysis, they might behave in different ways. So a control systems engineer might be interested in computing something like a sensitivity function. And I show them here. If you are not familiar with those concepts, it doesn't matter. The sensitivity function S is the transfer function from the reference to the control error. So typically we say, if I give a certain reference to my controller, we want the error to eventually become 0, right? We can't expect it to be 0 infinitely fast. That's unreasonable. But eventually, we would like it to be 0. But most of all, we don't want this sensitivity function to ever have a large peak, because that typically is associated with poor robustness. And when I say robustness, I mean things like we use a model for this analysis and the design. And models are always terrible, at least if you ask a control systems engineer. Yeah, I will always tell you that, no matter how much time you spend effort on your modeling, it's wrong, and we need to be robust with respect to how wrong it is. And the sensitivity function is a nice way of quantifying how robust we might be with respect to these errors. So the way this looks in code is that I ask Modeling Toolkit for get me the sensitivity in the point y, all right? So that gives you the output sensitivity function. For systems with single input and single output, it doesn't matter if you look at the sensitivity function in the input or in the output, but if those are multiple input, multiple output systems, it actually does matter. So you can ask for the sensitivity function in the point u also, and that would be a different function in general. So here I plotted both the sensitivity and the complementary sensitivity functions, and if you are a control engineer, you might be satisfied with this. It looks the way we would expect. In particular, we don't have any uncomfortably large peaks in these functions. So then you might be happy and say that this control design looks okay to me. All right, we can also ask for things like a loop transfer function. So the loop transfer function is the transfer function you get when you go one lap around the loop with one connection broken. So if I ask for a loop transfer here in y, what will happen underneath the hood is that Modeling Toolkit will actually remove this connection here. So I have a red cross. So in that case, the analysis point acts as a kind of a loop break. And that is very often useful for analysis. So the alternative way of performing this analysis would be that you yourself modify your model so that the connection is not there. But that's kind of a hassle, and we don't really want to do that. We just want to Modeling Toolkit to handle it for us. So the analysis point is a convenient interface towards that. Once I've gotten the loop transfer function, I package that into an SS. I call the SS constructor from the control system package, and now I have a linear system. I can compute things like the H infinity norm, so that would be the peak in the sensitivity function. Sorry, in this case, it's actually the peak in the loop transfer function. My apologies. I compute the H-infinity norm from the sensitivity function in the previous slide. And that peak is interesting because that's kind of a simple measure of robustness. And it also corresponds to this circle here in the Nyquist plot. So the peak is the peak of the sensitivity function is the inverse radius of this function. And if you're familiar with Nyquist theory, you might recognize that we want to stay far away from this called the critical point here. If this blue curve encircles this critical point, our feedback connection is unstable. So typically we would like to be far away from that point. And the reason we want to be far away is because this curve is associated with our model, and the model is wrong, so we don't actually know where the true curve is. And if we have actually linearized our system and nonlinear system, we know for sure that it's wrong because the actual system is not linear. So this gives you a very convenient interface between the nonlinear world of ModelingToolkit and the linear world that control systems engineers often perform their analysis in. Right, we can also perform simple analysis like compute gain and phase margins. So here I try to indicate with this green line, this point is where we would compute the phase margin, and the gain margin here is actually infinite because the curve does never intersect this real line. So this just to show that you can easily perform this simple analysis that you might be familiar with as a control engineer, even though you have a nonlinear ModelingToolkit model. All right, can you use this for more interesting systems, perhaps like a PD system? And the answer is yes, you can, and now the path is slightly more convoluted. We will not dive into great detail here, but we can model PD systems in ModelingToolkit. We might be interested in discretizing them, for instance, using method of lines. And after that step, we have typically a very large ordinary differential equation. We might want to linearize that, and then we have a linear version of that ODE. Typically, we might be interested in also doing some model order reduction if we do control systems analysis. We have a lot of those tools available to us in the robust and optimal control package. Things like balanced truncation and coprime factor reduction. So you can think of these methods as principal component analysis, but for dynamical systems. So they make use of the SVD and all that stuff. And no matter if we choose to perform a reduction or not, we might want to analyze this linear model. So we can do all the things we did for the previous control system example for PD systems as well. And if you are curious, there is a notebook on this QR code that tries to do this for kind of a very simple PD control example. All right. What are some other things we might be interested in doing? Very often we want to analyze our nonlinear system in multiple different operating points to make sure that we for instance, if we operate an aircraft, that is a nonlinear system, and the two most significant nonlinearities are related to the altitude and the forward velocity. So maybe we want to linearize this system in 10,000 different points in the forward velocity and amplitude space. And the linearization contains one step that is rather expensive. It's the structural simplification of the model that ModelingToolkit does. So we would like to do that preferably only once, and we can do that. So there are some utilities here in control systems MTK called trajectory statespace and batch statespace. And what they essentially do is they just perform the structural simplification once, and then you just linearize using forward if or something like that multiple times for multiple different operating points. And then you might be able to do, for instance, a gain scheduling design where you design multiple different linear controllers for the different operating points and you interpolate between them. And on the QR code here, there is an example that does exactly this. So there is a nonlinear system, linearize it in multiple different operating points, implement the linear controller and interpolate. And there is a ModelingToolkit component that represents this gain scheduled linear system that you can make use of. And there are also some utilities to help you treat a collection of linear systems as one uncertain linear system. So if you plot that, you get kind of a distribution of Bode plots that might be interesting to analyze. All right, we have a number of additional resources. There is, of course, documentation on the linearization in ModelingToolkit. Some of the linear analysis documentation belongs in ModelingToolkit standard library, and there is a particular reason for that. So the analysis points are inherently a causal concept. You have to have a notion of an input and an output for those to make sense. And ModelingToolkit is an acausal modeling language. So ModelingToolkit doesn't actually care about inputs and outputs. But there is this particular sub-library in ModelingToolkit standard library that implements blocks that actually are causal. So a PI controller is causal. It has an input and it has an output. So that's why it belongs there. There is a link to JuliaSim control. So it's our Julia Hub library for control that adds more sophisticated functionality on top of the open source control systems packages. We have a lot of linear analysis examples there as well. And then finally, there is a YouTube video where I go into a bit more detail about why we need the analysis points and why it's awkward to try to do this analysis without them. There is also some future work, and maybe you have seen the little demo at day one here about the graphical user interface we are working with. All of this fits very natural into a graphical user interface workflow. So you have your components, your block diagram there, you have your signals to name them and to ask for, give me the analysis, give me the sensitivity function in this particular signal, and to integrate all of that into a smooth workflow in the graphical user interface. All right, and that was my final slide. So with that, I would like to thank you for your presence.
Only one thing in this feature where everything else is done.
Yeah, for linear analysis, there is only so much you can do. When you linearize the system, you got it. And then what you do with that linear system, you can do a lot of interesting things with that. But
That's a quick question. So
yep.
If you have a model that, using forward diff or symbolic methods.
Yep.
If you have a model that you can't handle, generally decoding it symbolically.
Sure.
For some reason, what does it do?
Sure. If forward diff doesn't handle it, it will just throw an error in your face. And what we then suggest you do is you can do data-driven methods like frequency response analysis. So we do have such methods implementing in the JuliaSim control package. So that would be, if we consider forward diff the infinitesimal kind of linearization, this would be a finite kind of linearization instead. Yep. You could easily do that also. You could swap out a forward diff for finite diff if you would like to do that, yeah. Yep.
And there is a new type of decoding too as well, because of the JuliaCon compiler pieces.
Yep. So the actual linearization, we used forward diff there because it's simple. You can switch it out for the symbolic linearization because sometimes for small models that gives you some insight if you have linearized the nonlinear system symbolically. But there is nothing preventing you from doing any other linearization, yeah.
And if you have a model that has sort of a block diagonal structure where some blocks can linearize symbolically, other blocks that can't linearize, kind of stuck and you have to linearize the whole thing there.
In this case, yeah, we would be stuck there. We don't have anything special case to handle that. Yep. Yep.
For the analysis points, does that have to be specified within the ModelingToolkit model, or can you use more like generic statespace object or something to specify the analysis points and then do that?
So all of the downstream analysis, it doesn't rely on ModelingToolkit at all, actually. So you can, if you have a linear system already, you can already use this, the analysis tools. The analysis points only make sense in the context where you have these connections between ModelingToolkit points. If you don't have those connections, you are kind of on your own with respect to calling the lower level linearize function, where you just provide, here's my input and here's my output. But if you look at the video I showed there about the video on how to linearize the ModelingToolkit model, it's awkward to do that, especially if you have a model that simulates. That model does not linearize. And I go into the details why that is the case in that video. And it has to do with the structural simplification will consider your linearize, when you try to linearize, will consider that you have too many variables. Because now you add an additional input, but the model is already fully specified. So you kind of need to break, you need to unspecify the input before you actually perform the linearization. And that's the awkward part. It's awkward to work with. So the analysis point make that a bit easier. But you can do it manually if you want to. Yep. Yep.
Can you talk about what you do for the discrete side? Because at some point you're going to want a statespace system with your controller as well.
Sure. We do this. We had a... Yeah, we don't handle it, is the unfortunate answer. Yes. Yeah. Well, yeah, we handle the simulation of it, but it's not handled at all in the linearization, so we would have to add that, yeah. But obviously, we should do that, and we will, but it's not there at the moment. Yep. Yeah. Yeah, sorry to give you an unfortunate answer there, but that's the case. It will happen in the future. Yeah.
Future works better than not going to be worked on. So.
Yeah, yep.
Yeah, and it'd be interesting to have partners for which they want to actually use the things that are mixed and discrete and continuous. So if you have models or if you want to come work with us, come talk with us.
All right, cool. Thanks.